Take any smooth map that bends space and zoom in until the bending disappears. And all that's left is a flat linear stretch. That local stretch is called the Jacobian. 2 weeks ago, Anthropic put this exact idea inside a lens that reads what a model is about to say. This is J-spaces. Let's go deep. You already understand the Jacobian. You just know it by a smaller name. The derivative answers one question. Nudge the input a little. How much does the output move? It's the slope, the best straight line approximation to a curve at a point. Zoom into any smooth curve far enough and it looks like a line. The slope of that line is the derivative. That's the whole idea. The Jacobian is the same idea for functions with many inputs and many outputs. A robot arm turns joint angles into a hand position in space. A weather model turns pressure, temperature, and humidity into the rates of change. A neural network layer takes a vector in and pushes a vector out. Picture a map F that takes the whole flat plane and returns a new one. It deforms space. Straight grid lines curve, squares bulge into blobs. A single slope can't capture that. The map can stretch, squash, rotate, and share at once. We need a slope in every direction, and that grid of slopes is the Jacobian. Each entry just asks, when I nudge this input, how hard does that output respond? Stack those responses in the grid, and you've built the Jacobian matrix. Multiply a tiny nudge by j, and you get the tiny output nudge. It's the derivative as a matrix. Let's make it concrete. Take a simple map. U equals x plus 2y and v equals 3x. The partial derivatives are all constants, so the Jacobian is the same everywhere. Its determinant is 1 times 0 minus 2 times 3. So area is scaled by 6 and flipped. Zoom into one point of that warped plane until the curves flatten out. Drop a tiny square at the point and apply the map. The square becomes a parallelogram, tilted, stretched, maybe flipped. The columns of J are simply where the two edges of the square get sent. The determinant of J is the area of that parallelogram versus the original square. Determinant 3 means area locally triples. 1 preserves area, 0 collapses the square to a line, negative flips orientation. That's the R that appears when you switch to polar coordinates, the Jacobian determinant. Compose two maps and the stretches multiply. That's the chain rule. A network is just many maps composed layer after layer. Information streams forward through those layers, reshaped at every step. So the network's derivative is a long product of per layer Jacobians. Backpropagation is nothing more than multiplying that chain of Jacobians, and the vanishing gradient is those determinants shrinking towards zero. Which brings us back to Anthropic's Jacobian lens. It works like a detective's lens. Glide it across the model's activity, and hidden clues light up that were invisible on the surface. For every word, it finds the hidden activity that makes the model likely to say it, even several tokens into the future. That map is non-linear, so JLens replaces it locally with its best linear approximation. One averaged Jacobian per layer carry a hidden activation into the model's output space. Concretely, it's a matrix reading how each direction in the hidden state pushes on the output. Keep only its strongest directions, the top singular values. Those few high leverage directions span what Anthropic calls J-space, a small internal workspace, a few dozen concepts at a time. Albeit it and fluent speech survives, but multi-step reasoning collapses. Point that lens inward and you can drift through the model's mind as thoughts light up. But the real power is where you point it. Sweep the lens across the model's layers and you can watch a thought take shape. Early regions hold the surface words, deeper regions hold the plan. On a multi-step problem, the answer lights up inside J-space long before the model writes it. And this isn't hypothetical. In a real model, you can watch the ocean answer surface in its deep layers. It even caught the model suspecting it was being tested, a thought it never put into words. Point it at a model trained with hidden agenda, and the lens flags it on ordinary prompts. For the first time, you can watch a model think and check whether it's telling us the truth. Zoom out and something stranger comes into view. In cognitive science, one leading theory says that the mind has a global workspace, a shared blackboard many processes read from and write to. The unsettling finding is that J space behaves almost exactly like that workspace. Content doesn't fade in gradually. Past the threshold, it ignites, snapping into the workspace all at once. That sharp, all or nothing jump is the signature cognitive scientist called ignition. The workspace has a tiny capacity, only a few dozen items at a time, much like human working memory. Make the model juggle two things at once and they interfere just as they do in people. You can summon a concept into the workspace on demand and watch it light up. Steer the workspace and the model's own report of what its thinking changes with it. So to be clear, this is a functional parallel to a theory of consciousness, but not proof that the model is conscious. So here's the whole arc in one breath. A slope in every direction, columns say where the axes go, the determinant says how the space stretches. It's the engine under integration, robotics, graphics, and every gradient in deep learning. And now it's a lens we can point back at the models themselves. I'm J Spaces. See you in the next one.